Hello, this is Dr. Baxley. Welcome to the lecture video for Chapter 7, which talks about electrons and waves. This will be Part 1 that discusses the electromagnetic spectrum. Here's a quote from my favorite physicist, Richard Feynman. Well, he's my only favorite physicist. Richard Feynman worked on the Manhattan Project to develop the atomic bomb. He worked on the Challenger explosion investigation in 1986. He did a lot of things. Super smart, super talented. Pause the video and take a moment to read what Feynman said about small particles. So what Feynman said was that really small things don't act like things that we know about. I can't give you a lot of analogies about really small particles because they don't act like anything we've ever seen before. I'll try, I'll do my best, but it's not easy. In the whole history of the world, there's like 50 people that have ever really understood something called quantum mechanics, or the behavior of really small particles. I'm not one of those 50 people. There's also about 3 people in the world ever, including Feynman, that have been able to explain this kind of stuff to other people. I'm definitely not one of those 3 people either. I'll do my best though. I'll give you a few analogies, but be prepared to see some really weird stuff about small particles. In order to talk about electromagnetic radiation, we're going to start by talking about light. Then we'll transition into electrons because they have some of the same properties. In order to talk about light, we need to talk about waves. And waves have 5 important properties. Waves have a wavelength, or the symbol lambda, which is a Greek letter. And that's typically measured in meters, nanometers, or centimeters. Waves also have a frequency, which is the Greek letter nu. And frequency is the number of cycles that pass by a point in 1 second. It has a couple of different units. One unit is hertz, another unit is second to the -1. This is the same as writing 1 over seconds, where seconds is in the denominator. Waves have amplitude, which is just the height of the wave. We're not going to worry about that too much. The speed of a wave is given as the symbol c, and c is equal to the frequency times the wavelength, or c equals lambda times nu. The energy of a photon or a wave can also be calculated. A photon is just an individual particle of light, and the energy for every 1 photon is given as h times the frequency, or h nu, where h is called Planck's constant. Planck was a famous German scientist. We'll talk about him in a bit. And Planck's constant is 6.626 times 10 to the -34 joules times seconds. It's kind of a weird unit, joules times seconds. The speed of light in a vacuum, or c, is equal to 2.998 times 10 to the 8th meters per second. This is nature's speed limit. Nothing goes faster. It's a constant you should know. Here are a couple of figures from your text that show the different properties of waves in terms of wavelengths and frequencies. Each of these pictures represents a wave, and we can calculate the wavelength by looking at any one repeating unit of the wave. For example, we could look at a trough here and a trough here. This distance would then be equal to 1 wavelength. We could also look at the peak of a wave and the next peak of a wave. That would be the same distance in terms of wavelength, and we could look at it from maybe this spot to that spot. That's also the same distance in terms of wavelength. In terms of the frequency, if we had this wave moving over time, we could figure out how many wave peaks move through a given section of the diagram in one time. In the second picture, the wavelength is shorter in any space we measure. And in the third picture, the wavelength is shorter still. If we envision that this time unit was 1 second from the beginning to the end, we would see that a number of waves travel through that section in one time. In the first drawing, there are 3 wave peaks, 1, 2, 3. In the third drawing, there are 1, 2, 3, 4, 5 peaks. And the last drawing, there are 1, 2, 3, 4, 5, and then a 6th peak if we count the fraction from the first half to the second half on either side. So this would be 6 peaks per second. That would be its frequency. This gives us a relationship, a fundamental relationship, between frequency and wavelength. In that, from that formula we saw on the previous slide, C equals lambda times nu, if lambda goes up, the wavelength increases, the frequency of the wave has to decrease. That's because the product of those two values, wavelength times frequency, has to equal a constant. So if one goes up, the other one goes down. The picture on the right shows different amplitudes. This is a set of waves or a set of photons with a low frequency, and this is a set of waves with a high frequency. This is another figure from your book. This shows the entire electromagnetic spectrum. There's a lot on this chart, so let's break it down into little pieces and see what we can see. At the top of the chart are frequency values. In terms of the electromagnetic spectrum, there are gamma rays on one side and radio waves on the other side. The gamma rays have really high frequencies, and the radio waves have low frequency. The next set of numbers are wavelengths. The radio waves have long wavelengths in terms of meters, and the gamma rays have short wavelengths in terms of meters. And this goes along with that relationship that we saw on the previous slide, where C equals lambda times nu. So if the frequency is really high for gamma rays, their wavelengths have to be really short. This next figure shows how electromagnetic waves travel through space. All those different kinds of waves, UV, gamma, visible, radio, they all propagate through space as a wave that has an electric field component and a magnetic field component. Now the magnetic field component is a lot like the magnetic field you experience when you have a magnet next to a refrigerator. The electric field component's a little bit different, but they are connected. You might remember they're connected in 4th grade science class. You might have made electromagnets by wrapping some copper wire around a nail, hooking up a battery, and trying to figure out how many paper clips you picked up. Anybody ever do that? It's kind of fun. So the waves propagate through space like this. They have the two different fields. And here's a little app that'll show you what it looks like. So this app shows a couple of different things. The coolest part I think that it shows is how electrons move back and forth and therefore propagate electromagnetic waves from them. So up in the picture, the little blue dot moving back and forth is an electron wiggling and jiggling back and forth, maybe in response to some kind of electric or magnetic field. As that electron moves, it generates an electromagnetic wave that propagates away from the electron. The electron is charged, so it gives the wave an electric field and a magnetic field, and it moves around through space. This diagram can be moved to show the different fields. There's the electric, and there's the magnetic. You can see the electron zipping back and forth there. I can change the wavelength by sliding this little slider on the screen. And what will happen to the frequency as the wavelength goes up? You're right, the frequency changes as the wavelength increases. So now you can see that the wave, still moving at the same speed, has fewer wave peaks or wave troughs in a given amount of time. You can even count them. 1, 2, 3. Versus the shorter wave, 1, 2, 3, 4. It's a much faster count. Anyway, I like that app because it shows the movement of electrons and how it propagates waves. This is exactly what happens in your cell phone. Your cell phone wants to send a text to somebody, or an InstaChat or Snapgram, whatever they call them, and you press a button for send. The phone inside has a little antenna. It wiggles and jiggles electrons back and forth, and voila, it sends LOL to one of your friends. Here are some sample problems regarding wavelengths of light, frequency, and how they relate to each other. Pause the video, work these problems out with the formula you know from before. C equals wavelength times frequency, and come back soon and get the answers. Okay, for the first question, we can use the formula C equals lambda times frequency. We know what the frequency of the light is, and so we can solve for wavelength algebraically. Wavelength will be equal to C over nu. The speed of light is 2.998 times 10 to the 8th meters per second, a number you should know. That'll be divided by the frequency, 7.95 times 10 to the 14 seconds to the minus 1 is equal to 1 over seconds. The units of seconds then reduce to 1 and cancel out. And the answer would be 3.77 times 10 to the minus 7 meters. For the second problem, it's very similar. What's the frequency of light with a certain wavelength in meters? We can start with frequency equals c over lambda. That would be equal to the speed of light over the wavelength. And that works out to be 9.00 times 10 to the 7th seconds to the minus 1 is the unit. The unit comes from meters, reducing to 1 and canceling out, and the units in the numerator are left as 1 over seconds. To solve number 3, which has a longer wavelength, we might need to convert one of these values to another so we can compare them more directly. Let's compare frequencies. So let's convert the 585 nanometers of light to frequency and see where that gets us. First of all, if we're going to use the speed of light, we need the wavelength in terms of meters, not nanometers. So let's convert 585 nanometers to meters. That works out to be 5.85 times 10 to the minus 7 meters. We can then use the frequency formula to calculate frequency. This works out to be 5.12 times 10 to the 14th seconds to the minus 1. We can see that this wavelength of light then has the higher frequency, therefore the shorter wavelength. So this would have the longer wavelength, being lower in frequency. One other note about frequencies and wavelengths is that the angstrom is a historical unit that was used to measure wavelengths. And an angstrom is equal to 1 times 10 to the minus 10 meters. It's also equal to 0.1 nanometers. This is because nanometers and meters just weren't quite small enough units to measure wavelengths of light in, so angstroms are often used, especially in older literature. There are just a few more notes about waves. Waves can also have interference patterns. For example, the phases or peaks and valleys of a wave can be in phase, meaning they're in sync with each other. They can also be out of phase, where they're opposite, they're not in sync with each other. The wave patterns end up either constructively interfering or destructively interfering. So the combined effect of the in-phased waves is to have larger amplitudes, while the out-of-phase waves combine to have no amplitude whatsoever. They cancel out and there's no more wave. Pretty colors are a result of interference patterns. So seashells have that deep opalescent color, and peacocks have that iridescent color because of constructive and destructive interference patterns with light waves. One of the great big questions of physics in the last century was asking if light acted like a particle or a wave. When light waves pass through an open slot, they'll propagate. You can see this if you shine a flashlight through a crack in a window or a door. You'll see some light bleed out and illuminate the surroundings, and not just in a narrow path away from the hole. However, if you take a particle beam or a little ping pong ball gun and you shoot ping pong balls through a narrow opening, like a crack in a door, they'll go straight through and hit one single spot on a target. So what does light do? Well, light acts like a wave. So if you push light through two slits, you end up getting interference patterns. You'll get places where the waves constructively add up to be bright spots, and you'll get places where waves destructively interfere and cancel each other out. And so here's a little animation of the kind of pattern you get, where light waves are propagating, they move through two spaces, and then you get bright and dark spots on a detector or photographic film as the light either constructively or destructively interferes with each other. It's possible, though, to do experiments where light acts like a particle, and we're going to talk about that in the next video.